This is the FP2 paper from June 2020. Let's just go straight into it. A-level further maths, Pearson Edexcel and all that. Okay, no restrictions. Well, this is how many total members? 26 total members. If you're just choosing 8 with no restrictions, then that's just 26 choose 8. I do the choose notation like this, but however you want to do it, just type in 26C8 into calculator, you get this. What if the team must have 4 adults and 4 juniors? Well, then you have to take 4 from this port, that's 12 choose 4, multiplied by 4 from this port, that's 14 choose 4. Just multiply those things together and you get this, and then more than half the team must be adults, so you must have either 5, 6, 7 or 8 adults. If you have 8 adults, then it's just 12 choose 8, and then you're not taking any juniors. But of course that's just having 8 adults, but you could also have, so plus 7 adults, which is 12 choose 7, and then choose 1 junior from the 14, so multiply those together, and then you can have 12 choose 6 for 6 adults and 2 juniors, and then finally 5 adults, 3 juniors, times these all, or type these all into the calculator and then add them all together, and we eventually get this as our answer. And yeah, very, very nice, easy question 1 done, just using the choose function. Now we have a recurrence relation. Now this is a second order recurrent system. To solve these, it's exactly the same as solving a second order differential equation. You set up you ignore this 3n for a bit. You just set up the auxiliary quadratic equation that comes from this. That's 9r squared, we'll just call it minus 12r plus 4 equals 0. You solve this, this actually factorizes to a copy of itself, 3r minus 2 all squared, which means the only root is 2/3. You now just need to have memorized that if you have one solution to the auxiliary equation, then you write the complementary function, you write as un equals a plus bn into that single root to the power n. So you just need to memorize this form here, and we'll leave that there for now. We'll now pick up this 3n here. Now we need to write that in the form something like lambda n plus mu could be the particular solution that we're looking for this. Just double check that none of these terms exist here, and they don't, because this 2/3 is unique, so that's good. So we're allowed to use this. Like for instance, if this was a 1 to the n, then we'd just have bn terms already over here, which means we couldn't use lambda n terms, and we'd have to do some mess around, but we don't have to do that here, so that's fine. So we have this. Of course, if we can change the n to an n plus 1 to make this, and n plus 2 to make that, and we can shove all of this into here, which gives us this. And the reason I've done that is because if I expand and simplify it, I think I can solve for lambda and mu. I mean, it looks like a complete mess right now, but all you really need to know is that however many n's are on the left-hand side must be the same as the number of n's on the right. So there are 3 n's over here. So 9 lambda minus 12 lambda plus 4 lambda must be those 3 for the n's. So that's just looking at the n's, you can solve this. And then looking at the non-n's, there are 0 non-n's over here. And non-n's is 18 lambda, but you know what lambda is. Plus 9 mu, minus 12 lambda, and so on. You know lambda is 3, so that's 8 is 6 times 3 is 18. It's just those two terms, and then these simplify down to make this. And you get mu as minus 18. And so that's going to be our particular solution there, and then we can just combine that with the complementary function, and we get our answer. Now that's still in terms of a and b. I mean, I said at the start that's the same as a second order differential equation, isn't it? Because it is, right? You do this bit with a quadratic, then you do this bit where you substitute it into the actual thing, and you find some unknowns, and then you finally find the last unknowns by using the boundary conditions. So we have this as our thing, and now u1 equals 1. We'll just put that into here. u1 is 1, so that replaces with a 1. That replaces with a 1, and that replaces with 1s, and you get this. This makes minus 15, add to 1 is 16, times 3 is 48, divided by 2 is 24. And then next one we say u2 is 4, so replace that with a 4, and replace all these with 2's, and I think we get this. And yeah, okay, so again, minus 12 makes 16, divided by 4 is 4, times by 9 is 36, so we get this. Of course, the difference here is just b is 12, b is 12 and a is 12, I think is what you get eventually from these two. And then, of course, we can just write that with a and b is 12, and we get our final answer, which is good, 9 marks for something that's literally the same thing every single time, so that's good. Question number 3 is characteristic equation times. That's to do with the eigenvalues and vectors, isn't it? So we set up determinant of m minus lambda I. Maybe these should be in bold, but it doesn't really matter. Is equal to 0. This is where this characteristic equation is going to come from. So m minus lambda I. Well, I is just the identity matrix 3 by 3 to make this make sense. So we just take away lambda from the diagonals here. You'll be very used to this. You'll have seen this before if you've done any practice of this at all. And then determinant of a 3 by 3 is going to be this times the determinant of this bit, so this times this times this, minus this into the determinant of these four here, so this times this minus this times this, and then plus this into the determinant of these four. You eventually get something that looks about like this. You can verify all of my maths here if you want to. You very carefully expand out and simplify, very, very carefully. This is all just maths that you know, and you eventually arrive exactly at the thing that I want you to get, which is good. So we have that, and that's the 3 marks. Given det m is 5, so okay, that means we can actually just find what k is, right? Because we can go back to here and go, okay, determinant of that is 5, so 1 times this minus this is that minus k. There's always a minus there, remember, even if there isn't here. This minus this, which is this, and then minus 2 into this minus this gives you this, and then you solve that and you get k as minus 7. So that's good. So we can update our m to actually have a minus 7 in it. We can also update the characteristic equation. Putting in a 7 into here makes 14. Sorry, minus 14 plus 13 is minus 1. Minus 1 is plus 1. And yeah, same thing here. And we get this. Now, what the Cayley-Hamilton theorem says is that a matrix is the solution of its own characteristic equation always. So the characteristic equation is this with k updated. So that means m cubed plus m minus 5 is 0. So we can say that, we can quote that, and we can say this. And now it wants us to find m inverse. So how do we get m inverse out of this? By the way, I've written an I here as the identity matrix I, just because otherwise taking away 5 doesn't make any sense, because these are both matrices. So just take away 5 lots of the identity matrix to make it make sense. So where's m inverse come from? Because I've got m cubes and m's, but no m inverse. Well, just divide everything here by m, or just multiply it by m inverse. It's probably a more correct way of saying it. M inverse times this will just make m squared. M inverse times that is the identity, and then this will make m inverse. And that's great, because now I can just rearrange that very easily, move this over, divide by 5, and we get this. And this is something that I'm pretty sure I can work out, because I have m with a minus 7 in here. I can type this into a calculator to work out m squared, because I can't be bothered to do that by hand. You get this. You can add I. Now, adding I means adding 1 to the diagonals, because I is just 1, 0, 0, 0, 1, 0, 0, 0, 1. So just add 1 to all of these middle bits there, and you get this, and then just divide it by 5, which you don't have to do. You can just shove a 1/5 in front, and I think we'll get m inverse, and that'll be the entire question. So good. That is done. Question number 4 is just a great question. I really loved it. Just lots of really nice calculus, which is probably the best thing in A-level maths, isn't it? Let's be honest. So we've got a speed bump here, and we want to work out how much area is going to be painted. So let's create a plan here. We're going to need to find out this area here at the end, and we're going to need to double that because we're going to have 2 ends to work out. So, and this is this cross section here, so that means I need to work out this area. So okay, I'm thinking in my head I need this area, and I then need to double it, and that'll get me to both ends. Now, how do I work out this area that I need to paint on top? Well, this is FP2, so think in your head, what FP2 things do you know? Well, it looks a bit like a cylinder, doesn't it, I guess? And to work out the area of the curved surface of a cylinder, you say that this area, let's pretend it goes all the way around, would be 2 pi r, and then you just times that by the h, because you're almost imagining just unfolding it into a rectangle, right? So I think on the same logic, if I could work out the length of this arc here, and I think that's something FP2 tells me how to do, I can do a line, I can work out the length of a curve by doing this special integral that we're going to do. I can work out that length there, and then I can just unfold it and pretend that whole curved surface is a rectangle, and I'll just do that length times 2.35. And then I add it to the 2 ends, and I'll be done. So that's my entire plan. So let's go back to the start and say, okay, the first thing I wanted was the area of this. Now this is a polar equation, so you actually need some CP2 stuff, some Core Pure 2 book stuff, which is the area of a sector in this sort of polar idea here. We can just do a half r squared, the integral of r squared. So, and of course we can see what are going to be our limits. Well, if theta is 0, you just get r is 30, so that just 0 is heading off in this direction, so r is 30, so that's there. And then theta is 1, where you just get r is 0, so that must be here, right? So all we have to do is integrate between 0 and 1 of half r squared. Now r squared is 900 times this squared, but the 900 just can go out the front, times by half is 450. And of course I can just square that out, right? That's not hard to square out, and I can just integrate that. So I just integrate it, I put in the numbers, and eventually you get this. And I said before, didn't I, that I wanted 2 of those. I wanted this area and this area over there. So I think I need to double that and say 480 is both side bits. And I'll park that there for a second, and then I'll say, okay, well, I also needed this top bit. And my plan, if you remember there, was to work out the length of this arc here. So look in the formula book again. Polar form is this one down here, so this is what I'm going to need. So I'm going to need dr by d theta. Well, that's not hard to get, right? Just differentiate that with respect to theta. I also need to square that. Well, that's also not hard. That just makes that. And I also need r squared. Now, r squared I essentially already worked out. It's 900 times this squared, which is that. So it's 900 into that. Okay, and I can just put that into the integral here. So I think I can put that all in. So that's roots 900 into that. That's r squared. And then plus, then this thing here is dr by d theta squared. I can factorize out a 900 here from both these terms to just leave a 4 left behind. And then, of course, I can do root 900 times root of all this, because that's a product. But, of course, all of this simplifies to just make a plus 2 theta squared from those two terms. And this is obviously 30. This is also really nice because this factorizes, I think, to 1 plus theta squared all squared. And then, of course, the root and the square can sort of just cancel. They don't really, but they can in this case. And yeah, this is super easy to integrate. You put the 1 in, the 0 doesn't matter. That makes 4/3. Divide by 30 is, times by 30 is 4 times 10, which is 40. And that's the length of this arc here. And so that's 40. I decided I wanted to times that by 2.35, except I don't, because this is in centimeters and this is in meters. So I think I actually need to do 40, which is this arc length, times by 235 to keep it all in centimeters, because that's what it's asking here, which gives me this, and then I just add that to the 480, and we get our final answer, which I think is correct and is good. I just really enjoyed that question. I thought it was really nice. Question number 5 is another question that's really nice. This paper I just thought was really pleasant overall, because it just had a lot of stuff in here that you just should have practiced. So the last two questions I thought were some of it was quite harsh, but anyway, this one's quite nice. The first step is you just rearrange this for z. So I won't cover that in very much detail because it's just GCSE rearranging. And then you just shove that z into here. And now there's a few things to be right about this. You can times this one by w plus 3 over w plus 3 to make this, and then of course we can combine the fractions together. When you have a mod of a fraction, you're just allowed to take the modulus of them separately, and then of course you're just allowed to multiply this modulus over there. And this is basically exactly what they're asking us to get, right? Except I just need to factorize this in the right way, and we'll have what they wanted me to get. So that's good, that's done. Hence find this. So again, you should have practiced this. You just write w as some rectangular complex number like x plus iy, and then you just shove that into each of these two things here, which is what I've done. And then yeah, you do some simplifying, where simplifying is very able to do, and you also want to group the complex things and the non-complex things together. So I've just expanded this out, but here you can see I've grouped the x plus 3 because that's not complex, and the iy on its own, and I'm going to do the same thing over here. And the reason I'm doing that is because the modulus of, say, a complex number like a plus bi is root a squared plus b squared. But if I square both sides here, I'll get this. And so if I square both sides here, now the 3 has to square separately, so that becomes a 9 on its own. But this is a modulus squared, right, of just sum a plus bi. So this is just a squared plus b squared, so it's just this squared plus this squared. So there's no expanding out to do here, and the complex number goes away, which is perfect. That's exactly what I want. And the same thing here, this squared plus this squared without the complex number. And then, of course, it's just a load of expanding and simplifying, which I won't bother going through very carefully. I've done everything in decimals because I just had my calculator app on my phone next to me, and I honestly couldn't be bothered to type any fractions. I don't think you'd be penalized for doing it like this. If you want to be more mathematical, you can maybe just get out some fractions and do it properly. But certainly you wouldn't get penalized for saying the center of the circle is minus this, right? That's obviously right, because these are exact. When you root this, I think a calculator will give you in exact form. You have to root it, of course, because this is r squared. So the radius you have to root. I never actually checked whether a proper calculator will give this. I just got this from the mark scheme. If you had been doing it properly, of course, you'd have got this quite naturally, but I think a proper calculator would root that to make this, I think. I haven't checked. Maybe you can check it in your own time, but I think it would probably do it. Even if it didn't, even if you just rooted this and left it as a decimal, the answer, I couldn't see anything in the mark scheme or in the question that would say that that's not correct to do. It doesn't say exactly anywhere here. So yeah, the mark scheme said this, but I think you'd get away with a decimal if you had been being lazy the entire time. Question number 6, so we have the shape here, and we've got some stuff we can do to it to, transform it and to do these permutations and stuff. So this represents 1 going to 3. So 1 becomes 3, 2 becomes 4, 3 becomes 5, 4 becomes 6, and so on. Well, that's just a rotation this way, right? You're just rotating the shape around. And because the grey bits will go from here to here to here to here, and the white bits likewise, it's not going to look any different, except the numbers will just be in a different place, which is kind of what you want by this. That's what this permutation is wanting, right? Is to make the picture look the same, just with the numbers in different places. So a rotation, it's 120 degrees, isn't it? Rotation 120 degrees anti-clockwise from the center of the shape will get me the marks. It's also worth mentioning that 60 degrees doesn't work, right? Because that would put this shade bit here, which would change what the shape looks like. So that doesn't work. So yeah, 120 degrees. Now it's asking us to come up with other ways of doing that, of transforming the shape, but leaving the picture looking the same, just with numbers in a different place. Well, you could of course rotate it clockwise at 120, right? And if you rotate it clockwise, 1 would go to 5, 2 would go to 6, 3 would go to 1, and so on. So that's what I'm doing here. So that's a rotation clockwise 120 degrees. So that's the first one. Other things you can do, well, you can put a mirror line here, and you can reflect it around that mirror, because this grey bit will go here, this grey bit will stay where it is, and all that will happen is 1 will stay where it is, 4 will stay where it is. So that's 1 and 4 staying where they are. And then 2 will swap with 6. Which is there, and then 3 will swap with 5. But you could also do that same reflection just along a diagonal line like this. So 5 and 2 stay where they are, and like 6 and 4 swap, and 1 and 3 swap. And then you could also do a reflection along this diagonal line to make 3 and 6 stay where they are. 2 swaps with 4, 1 swaps with 5. So that's those two things there. And then of course you've also finally got the thing that doesn't do anything, the identity almost, where 1 just stays where 1 is, and 2 and so on. And these I think will be all of them. I'm looking at 4 marks here. I'm pretty confident I'd probably get 1 mark for each of these, and then there's just the identity to name for the last mark, something like that. So I'm pretty happy I've got them all. I think if there were more, it'd probably be worth more marks. Is my logic in my head to say that I've got them all? But anyway, explain why each of the statements is false. G has a subgroup order 4. Now G has 1, 2, 3, 4, 5, 6 elements in it, so it's order 6, right? Now there's a theorem called Lagrange's theorem, which you don't need to prove, but you do need to be able to state, that says a subgroup's order must be divisible by the order of the original group. Now 4 isn't divisible by 6, so there can't be a subgroup order 4 existing anywhere. And that's all you need to say. It's just 1 mark, isn't it? Because it's 1 mark for each of these two things. So you don't have to get much in detail. Just say his name, say his name, and then just say that. And then G is cyclic. Well, that just means that a group could be generated by one single transformation done like lots of times. But when you look at these transformations here, or permutations, I should probably say, none of them are going to be able to create all of the others, right? Because there's two different things. There's the reflections and the rotations going on. Like the rotations move every single number, right? Like every single one moves to a different place, which means you can't possibly create one of the reflections where 2 of them are always staying where they are, no matter how many times you do the rotations. Of course, when you do the rotations 3 times, you just end up back where you started, so it doesn't do anything at all. And the reflections, of course, always keep 2 where they are. So no matter how many times you do those, you're never going to get the rotations. So and you could say that it's only 1 mark. All you have to do is just say what a cyclic group is and say that it doesn't do it. But if you wanted to give some extrapolation there about, exactly why it's not going to work, you could say that as well, just to be safe. And then it says you've got a shape here. Can you shade it in such a way that the shading is isomorphic to the cyclic group of order 6? Now, isomorphic means just basically the same. Like, it just means it looks a bit different, but when you look at the actual, like these things here, it just all looks the same as the cyclic group of order 6. Like, it's just the same group of things. Now, I misread this question and was trying to create a shading that was isomorphic to this group, but that's not what I was saying. Isomorphic to the cyclic group of order 6. Cyclic group of order 6, you can write a bit like this if you want to. This is how I think of it in my head, where one element is just generating all the other elements by just being done a bunch of times. So the other elements aren't really unique in a sense. They're just you've just taken this one, maybe transformational permutation and just done it a bunch of times to get all the others. So is there some shading you can do whereby just one movement you can just repeat over and over, and you can get every single movement in the possible, and there's exactly 6 of them? Well, I can't be bothered to shade this myself, so they've just offered these 2 solutions here. And this one's nice, I think. Notice how if you rotate this 60 degrees, you can then just rotate 60 degrees again and again and again and again and again. You go back to where you started. And also, that's 6 things, which is good. And there's no other things, because you can see here, as long as you shade it so it's not reflectional anywhere, that means you don't have any more of these kind of permutations you could do. There's only the reflection ones you can do to make this look the same over and over again. So just rotating 60 degrees clockwise will just get you all of the other elements if you just do it enough times. And those are be the only ones possible because there's no symmetry anywhere. So yeah, that's quite a nice shading, and this one also works for the same reason. And good, that's the entire question. Question number 7 is, I think, the hardest, or at least the first bit is the hardest thing in this paper for sure for me. I actually had to use the mark scheme to help me out because it's just a wild trick that was just incredible to see, but I didn't come up with it myself. So we've got this here. Now, the first thing you do when you're doing this kind of reduction formula is you want to do, usually, almost always, you do an integral by parts first. Right. Now, when you look at this, you have a problem because integral by parts won't work because there's only one object here. So we do our usual integral by parts trick and we just times it by 1. And now the idea will be, let's integrate this 1 a couple of times, and then let's have this as the other function that's going on. So, okay, this is going to be integrate the 1 for an x, leave this function alone, take away the integral of, integrate this one still for an x, and then differentiate this one. Minus n comes down, this differentiates to minus 2x in the middle, and then that becomes a minus x minus 1 over there. So, okay, that's integral by parts done. Now, how did that help? And this is, I mean, I did that and I was happy with that. I tried lots of other things and found it really hard to make progress. So, I mean, there's a few things going on here. Firstly, this n plus 1 is wrong because it should be an n and then n minus 1 over here, shouldn't it, usually? So maybe I've just done this wrong to start with. Maybe I should have immediately wrote down n plus 1 and replaced that with a plus 1 and then done it from there. But I figured there was probably a way to make this work without doing that. So I got to here. Now, I've written this really weirdly. Usually I would put the minus out here, but there's a really, really, really interesting trick here that gets this done, and you need to keep it as a minus x squared in order to do it. You just have to go full black pen, red pen. Full black pen, red pen. Shout out to black pen, red pen. And write minus x squared as 4 plus minus x, sorry, 4 minus x squared minus 4, right? Because 4 minus 4 is nothing, so this is the same thing as this. And now I've colored this in red because what's going to happen here is I'm going to expand this out, but I'm going to expand these two out together with this. And of course, when I expand this out together, I just increase this by 1 again to get to a minus n, and then I'm going to expand out this on its own to get minus 4 lots of this. So that makes that. So just take these two terms together and expand them out into here, increases that by 1 to make it there, and then the minus 4 lots of this just makes minus 4 lots of this. And that's really, I mean, I don't know how you were supposed to spot that. I mean, I know it was the hardest thing on this paper, and I know it's like the second last question on an A-level further maths paper, so I understand it's supposed to be hard, but that was, I mean, it's a great trick, but it would have taken me a long time to think of that. But yeah, watch some black pen, red pen to get better at spotting that kind of thing, because he does it all the time and it's great. Anyway, so yeah, now this integral can split up. We can just do 2 lots of this and then minus integral of that. So that's fine. So I just split this up, and then this here, of course, is just in, isn't it? Because it's just, I mean, it's just written there. That's in, so that's good. And now here, again, another place you have to be careful of in this question. It's really tempting to look at this and go, oh, well, that's just in minus 1, isn't it? Well, bring the 4 out, obviously. In minus 1. No, it's not. Because if you put a bracket around this, this actually turns into an n plus 1, right? This is just copied down from what we were looking at before. That's actually an n plus 1, because minus makes that, or minus plus makes that minus there. So bring the 4 out, and say this is in, and this is in plus 1. And that's amazing to see, because that's where this comes from here. So now we literally just move this over, we get this, and then divide by a10, and we get the answer they wanted us to get. I think that's a ridiculous question. I mean, what I would say, I haven't actually tried this, but what I would say is it's probably possible to start here on some scrap paper and just work backwards. Like, these are quite logical steps to make, aren't they? So obviously times by a10, separate the in's, and then write them as 2 integrals, and then maybe you can see where the whole thing was coming from. But I think even that's a stretch as well. But I mean, that was a tough question. But however, 5 marks for doing that. Even if you didn't get it, you can still use this here, right? So for the second part of this question, they've given you the answer to the first bit, so you can still pick up these 3 marks. So find I2, we'll just replace n with 1 everywhere you see an n, just replace it with a 1. And yeah, now this simplifies, and this simplifies to this, and of course I1 is just this integral with a minus 1 there, So now what we have to do is think about how to integrate this. Now, there's no reverse chain rule going on here because this is there's no x term here which would help you out when you integrate this. Also, when you erase -1, you get to a 0, so that definitely no reverse chain rule going on. I'm being an idiot. I actually am really frustrated at myself because what I did was I thought I was being really clever by factorizing this to 2 minus x, 2 plus x, and then I thought, oh, I can just do some very quick partial fractions and I'll be able to smash this out. We all know how to do partial fractions, so I'm not going to do it in too much detail. But you get this and this. Of course, you can then write it like this. It's 1/4 of this and 1/4 of that, but I just put the quarter out to make it 32th there. And then, of course, these integrates to log of this and log of that. Log of this has a minus because of this minus here, and we get this. The minus because, of course, if you think about differentiating this, you end up with a -1 at the top, which cancels that minus to make it plus again. And we get this, and of course, there's also a plus c. Don't forget that. I also forgot that, so I would have probably lost the mark anyway, I think. And then I looked at the mark scheme to check whether I was right, and it turns out I could have just looked in the formula book because this formula exists where a is, of course, 2 in this case. So you just say 1/4, and then 1/4 times 1/8 gives you 1/32. And then you have this log here. Of course, this log minus this log, you do these divided by this inside the log, so you get this. And you could have also just written down as arctangent, which would have been even faster. So I'm just annoyed at myself that I didn't look in the formula book as soon as I saw an unfamiliar integral. That's always the first thing you should do. But I guess it's nice to be able to do partial fractions for sure anyway, isn't it? And you get this anyway, but whatever. Moving on to the last question. We've got, okay, so n is this. So standard thing to do here is to write n as 1000a plus 100b plus 10c plus d, because that's, of course, how place value works. N is 3 mod 7. So if we mod 7 this entire thing here, 1000 is 6 mod 7. You can just, the laziest thing to do is just type 1000 divided by 7 into your calculator and see from the decimal which remainder it is. Like it's 0.8 something, so it's remainder 6. And likewise for this and this and this. Okay, so cool. So that's that. And actually that's 2 marks for saying that. So that's cool. And that's congruent to 3, isn't it? Because n is congruent to 3, it tells you. Good. So that's 2 marks for that. Use properties 2, 3, and 4 to show this. So 2 says n is divisible by 9. For a number to be divisible by 9, the digit sum has to be a multiple of 9. So a plus b plus c plus d has to be equal to, you could write something like 9m where m is an integer, but it's better to just write like either 9, 18, 27, or 36. The biggest that a, b, c, and d can be is 9, right? So 9 plus 9 plus 9 plus 9 is a maximum of 36. It can't be any further. So it's one of these 4 options. These are the only multiples of 9 they can be as a sum. Good, and then the first 2 digits have the same sum as the last 2. So a plus b equals c plus d. B is smaller. Now this tells me a few things. Now, if a plus b was odd, that would make c plus d odd, and then odd plus odd is even. If a plus b was even, then that means c plus d would be even, and even plus even is even. So in any case, these can't add up to 9 anymore, and they also can't add up to 27. But also, b is smaller than any other digit. The only way to make that 36 was 9999, but b is smaller than the others, so you can't make 36. These definitely add up to 18, which means each of these add up to 9. And I think, oh, that's 4 marks, good, okay, cool. And c is even is the final thing they're telling me about, which I assume that I need for this down here, maybe. So okay, this is a mod 7 thing. This is the hardest bit in the question for sure, but it's only 2 marks. I'm not sure how it's only 2 marks, but it is only 2 marks. So the mod 7 thing means I should probably focus on this. Now let's combine a few things I've got here. Firstly, a plus b I know is 9, and I also know c plus d is 9. So I can break this into 4 lots of a plus 2 lots of a plus 2 lots of b, because I know 2 lots of a plus b is 18. And I've done the same thing here, because I know c plus d is also 9, which makes this and this 27. Which is cool, right? So now I can, well, 18 is 4 mod 7, and 9 is 2 mod 7, so that together makes 6 mod 7, or 27 is also 6 mod 7, you can write. Take away 6 from both sides. Now, I could write this as 4 mod 7, or I could write it as minus 3 mod 7. I'm gonna do the latter. We look at this and we think, how the hell have they got this? Where has the 5 come from? There's not 5 A's here, there's 4 of them. Like, what's going on here? And the trick is that mods are funky, right? That's the trick. That's the only trick here, is just knowing that when you're working in the mod world, you can just do some weird stuff, right? So, okay, well, let's take away 4a from both sides. Now, usually in the normal number land, we would just divide both sides by 2 here. That's not how mods work, right? That's not how we get to C. How we get to C is, or one copy of C, is by multiplying until we arrive at something that's 1 mod 7. So if I multiply all this by 4, 4 times 2 is 8, which is 1 mod 7, so we'll just get to C. So if we multiply this by 4, I'll just get to C. And that multiplied by 4 is minus 16, and that multiplied by 4 is minus 12. But of course, and likewise, 2 times 4 is 8, but 8 is 1 mod 7, so that gives me the singular C. Now, minus 16, if I add a couple of 7s to it, add a 7 to get minus 9, add a 7 to get 2, add a 7 to get, minus 2, add a 7 to get 5. So that's where the 5 comes from, so that's cool. Minus 12 plus 7 is minus 5, plus another 7 is 2. But I'll leave it as the minus 5, and the reason I'll do that is because, of course, I can just factorize out the 5, and I'll get what they want me to get. So just play around when you have mods, because sometimes you can arrive at quite surprising results that are written in ways that don't seem like they'd obviously arise. But just play around with it, and you'll eventually regret it. Good. Question D is the final bit in this paper, hence determine n, verifying that it is unique. So let's just make a table. We have a bunch of restrictions here. A plus b must equal 9, so let's just go with 9 and 0 first. Now, if a is 9, we use this thing here. There's a reason they asked us to get this, and even more importantly, they've given it to you. Like, just like in question number 7, where they gave us the end of part A with that horrible reduction formula, it's super important if it's important enough for them to have given it in the question and not trusted you to get there on your own, then it's really important. So let's use this. So A is 9, means that C, 9 minus 1 is 8, times 5 is 40, 35 is 0, so this makes 5. So C must be 5 mod 7, right? Which makes D 4, because 5 plus 4 is 9. However, what's wrong with this? Well, C must be even. So this 9054 doesn't work, so I've crossed it out. Next, we'll just go with 8 and 1 for A and B. That's the next integer that actually adds up to 9, isn't it? So if A is 8, we get 7 times 5 is 35, so that makes 0, congruent 7, so that's 0. But that doesn't work because B has got to be the smallest thing. So that's not going to work. Whatever D is, that doesn't work either. So next, 7 and 2. Now C, so 7 minus 1 is 6, times 5 is 30. 7 times 4 is 28, so that's going to be 2 mod 7, which means D is 7. But again, B isn't the smallest, it's the joint smallest here, so that also doesn't work. B is smaller than any other digit. Next is 6 and 3. Of course, 6 minus 1 is 5, times 5 is 24, which is 4 mod 7, so D is 5. And I think this actually works, right? Because C is even, so that's good. B is smaller than the others, so that's also good. The first two digits have the same sum as the last two, both 9, that's fine. N is divisible by 9, well, of course, these add up to a multiple of 9 because they do separately. Now, N equals 3 mod 7, we actually haven't checked that. Let's go right back to the top here. Although I think maybe it's just a natural consequence of this because I used this to get down to here. So actually, I have checked it, right? But actually, thinking about it, I don't think I needed to. I think this is guaranteed to make this work here, because to get this condition, which is what I used to make that digit, we used this in the first place. So I don't think I actually have to check this, but I have done anyway. 36 plus 6 is 42, which is a multiple of 7, so that just goes away. 12 plus 5 is 17, which is 3 mod 7, so that's definitely correct. So that works, and then we just need to verify it's unique. The only other thing worth trying is 5 and 4, because you can't do 4, 5, because then B is automatically not the smallest digit anymore. So this is the last one to try. Put in 5 in here. 5 minus 4 is 5 minus 1 is 4, times 5 is 20. That makes 6 mod 7, so D is 3, but that's not the smallest digit anymore, so yeah, good, that goes away. And our only answer is that, and that's the entire paper. So yeah, thank you for watching, and I'll see you next time.